So, so let's begin today session. So this week all about the weld bead microstructure, how this weld bead appears in terms of microstructurally properties, hardness wise, and any phase wise changes, how it changes when we do the welding during the mm, how we do microstructure changes during the welding process. Okay, so let's first recap what is done to this week. Okay, weld joint varies metallurgical structure from point to point with the consequential variation in mechanical properties. This is because of development of temperature gradient. So, as we seen, suppose if I consider a TIG welding, it will generate a almost TIG arc. This is the welding arc tip, electrode tip. This is the workpiece. Okay, so this is the how arc is generated. So in this arc, the temperatures reaches around 5000 degrees centigrade, or more than 5000. So which will melt every material, any material, any element, any material. Okay. So the microstructure. So once we see the weld bead, so we have a molten pool here and followed by a. So we can increase this height. Okay. So here is the molten metal and here is the HEZ and here is the base material. So if I made a one straight line from here to here, if I make a temperature plot of this one, that straight line, if I measure a straight line at this point, this point, this point, and so on, this zero is the at the starting here point. Okay, so temperature profile will be looks like this way. Okay, so here is the fusion zone. If in the iron case, so it will be this is the this point will be the nearly 1500 degrees, and this point will be the heat affected zone. It will be the around 700 degrees. Okay, so it is above recrystallization temperature, heat affected zone. Here is the fusion zone. So above this point here, every element, every iron element, every element will be in molten state. Once we crosses this solidus line, here it will start. It will be not melted, but because of it is above recrystallization temperature and below the liquid state temperature, it will have a microstructure will change significantly compared to the base material. Okay, after this point there is no change in the microstructure. Okay, the extent of the zone depend upon the various factors like heat input per unit time, welding velocity, physical properties of the material. Okay, So the factors are, it will be affected by different factors. One is heat input per unit time. So if I see in case of oxyacetylene welding, heat input is much more slower as we seen previously. Heat input per unit area is much lesser in case of oxy fuel welding. So to reach the molten state, we have to provide this heat input for a very long duration in case of oxy fuel. So in that case, the reason of the molten pool and heat effect zone will be much more higher. Okay. But if in the case of increasing, and if we come for laser or electron beam welding, heat input is very high, so that within a fraction of time it will melt, and heat effect zone also will be very small, because there is less time to this molten heat to diffuse to the base material, so that the molten region will be small and heat effect zone also will be small. But in this case, oxyacetylene welding case, because of the higher amount of the time of exposure, lot of the heat will be dissipated to the workpiece, which results in broader heat affected zone. And welding velocity, if we increase the welding velocity, the heat effect zone will be small. If we reduce the welding velocity, then heat effect zone will be more, because of the, if reduce the welding velocity, more amount of the time it is exposing to the workpiece. Okay. And physical properties, what is the physical properties? That is, what is the melting point of this material, and what is the size of this material, and what is it heat thermal conductivity, what is, are we providing any cooling environment or not, what is the ambient temperature, all of these factors also will affect the, what is the amount of the heat affected zone, or microstructure will change. Okay. The weldment can divide into three distinct zones: weld metal zone, heat affected zone, and unaffected zones. Okay. As we seen here, we can divide them into three zones: weld metal zone, heat affected zone, and base material. Okay. So it is a, in the case of heat affected zone, the microstructure changes only for the certain kind of materials, like which are the polymorphological transformation, which shows the polymorphological transformation. That means with varying the temperature, the microstructure will be changes. For example, iron, we see the alpha phase, gamma phase, and paralytic phase, and different phases with varying the temperature. In that case only, we will see the difference in microstructure in heat affected zone because of this uh, heating process. But in the case of alloys which do not show the polymorphology transformation, that means whatever the phase which is present at the room temperature, the same phase will be continue for the even the until the melting point temperature. So that kind of materials we do not see any the microstructural changes, phase changes, but we can see the coarsening of the grains and relieving of the stresses. That kind of things we can see in case of volatility. Okay. So we can see some of the problems based on this one. So that time we can discuss further more into what is this aspects. Okay. So here is the first problem. In a fusion welding joint, the region that completely melts and solidifies during the welding called, what is it? Heat affected zone, weld melt zone, or fusion zone, or partially melt zone, or base material. I think we have seen here. This is the region where material will be completely melts, and it is the will not melt, but it will reaches above the recrystallization temperature, and above that is called the heat affected zone. And after that, this one is called the base material. Okay, so answer will be the welded metal or fusion zone. Okay, fusion zone in the region where the base metal melts due to welding heat source, then resolidifies. It often contains the columnar form of grains during the solidification. I think this is we have seen the. So this is how the microstructure will be looks like. So columnar grains we can see at the weld bit, and coarser grains near the heat affected zone because of the above recrystallization temperature. More time it will expose to the high recrystallization temperature, so the grains will start to merge and growing. And then after base material, we will not see the any microstructural change. Okay. So answer will be the weld metal slash fusion zone. Next is the which zone in the fusion welding weld joint experiences the microstructural change without melting. Okay, I think we have seen. So here asking about without melting. So fusion zone will change the microstructure, but it will melt and solidify. That time it will change the microstructure. Heat affected zone, yes, heat affected zone will not melt, but in solid form itself, it will reaches above recrystallization temperature. So that time it will changes its microstructure. Next, weld metal also same, it is the fusion zone only. Next, solidification zone. No, that is also not. So answer will be the heat affected zone. The heat affected zone is the area of the base material adjacent to the welding that experience thermal cycle but does not melt. Okay. The change may include the grain growth, phase transformation, reduction or increase in the hardness, and HZ properties of often control the strength and toughness of the weld joint. Okay. The partially melt zone PMZ lies between the where the partially melt zone lies is the. So if we see, so this is our workpiece. This was the fusion zone, and this is the heat affected zone. So between the fusion zone and heat affected zone, if we see, if we draw a small line, so this will be the partially melted zone. As we seen in iron carbon diagram, at 1500 degrees centigrade, there is a phase, there is a place where alpha plus delta plus liquid states will be present, because so that is will be present here. This is the partially melt zone. Okay, some portion will be in the solid phase, some portion will be the um, liquid state. Okay, so that solid phase will be act as a nucleation point for the this columnar grains to form. Okay, so this is called as a partially melt zone. Okay, answer will be the fusion zone and HZ. Okay, between the fusion zone and HZ. Okay, the partial melt zone is very narrow region between the fusion zone and HZ, where grain boundaries may partially liquefy and temperatures exceeds the solidus but below the melting. Those zones often prone to liquidation cracking. Okay, next. Which following zones typically exhibits columnar grain structure due to directional solidification? I think this is also we have seen. So which zone we can see the columnar grains here? It is the fusion zone. So in the fusion, answer will be the fusion zone. In fusion zone, molten metal solidify under the a temperature gradient leads to columnar dendritic grain, because In welding process, the temperature reaches to thousands of degrees in a fraction of seconds, and it will again cools to very low temperature is also in fraction of seconds. So the time is available for the microstructure to form is the much more less, so which makes it forms the columnar grains. Okay, so the columnar dendritic grains growth towards the heat flow direction. This typically means fusion welding process such as the gas welding, SMW, and so on. Next is the which is the following zones in fusion welding is least affected by the thermal cycle. So which zone is the least affected by the thermal cycle? So here is the fusion zone, here is the partially melted zone, here is the heat affected zone, and here is the workpiece. So the base material zone. Here the base metal zone will be the unaffected one. Okay, so here you can see fusion zone, heat affected zone, partially melted zone, and unaffected zone. Unaffected zone will not experience any change. Okay, the base material is the parent material far enough from the welding so that it does not experience significant temperature rise. Okay, thus microstructure remain unchanged. That means it is the temperature it reaches, but it is below the recrystallization temperature. So the microstructure does not change. Mechanical properties remain same as the original material. Okay, next. So there is the two condition is there. The heat affected zone may exhibit the grain coarsening. Reason it is giving the material in heat affected zone experiences high temperature but does not melt. So answer will be, so is reason correct or not, that we have to see. Okay. So both A and R are true, but R is the correct explanation. Heat affected zone may exhibit the grain coarsening. Yes, answer. Heat affected zone we can see the grain coarsening. Reason, what is the reason giving here is the material in HEZ uh, experience high temperature but does not melt. Okay, so answer will be both A and R, but R is not correct. A true, but R is false, and A false, but R is true. Answer will be both correct. In HEZ, the metal experience temperature close to the melting point, but without melting, causes grain growth, phase transformation. So thus reason currently explains the assertion. Okay. So following are the some of the key points that we have to take away from from this uh, portion is that fusion zone melting occurs, partially metal zone we see the only partially it will melt, and heat affected zone there is no melting, base metal zone there will be no melting. The key features is that uh, fusion zone we will see the solidified weld metal that is having the coarser grains, and partially melt zone liquidation possible, and heat affected zone microstructure changes, and base material there is no change in the microstructure. Okay. Next, the heat affected zone in the welding joints is the region. What is the region? The metal that melts and solidifies during the welding. No, because in heat affected zone there is no melting takes place. The experiences the thermal cycle without melt. Yes, that is also because it reaches the thermal cycling, but it will not get the belt. And see, the contains the filler materials only. No, that is also not the reason, and that remains completely unaffected by the weld heat. That is the base material. So answer will be B. Okay, that experiences the thermal cycles without melting. Okay, the heat affected zone is the portion the base material adjacent to the welding that is heated during the welding but does not reaches the melting temperature. Okay, so due to thermal cycling it undergo grain growth, phase transformation, change in the hardness and strength, thus microstructure change without actually melting. You can see here, so heat effect zone is a part of the weld joint which heated up to the solidest temperature of the parent material. Okay, this is results into various degree of the influence on the microstructure because of heating and cooling cycles. Okay, depending on the peak temperatures reaches, the HZ in the steels are divided into different zones. So how we can define HZ is that it is the between the line between the solidest temperature to recrystallization temperature, okay, of the parent material. Okay, so what is the three zones you can see here? Grain growth zone, recrystallization zone, partially transformation zone, temper zone, and unaffected zone. Okay, grain growth zone, there, which is the reason we can see the coarsening of the grains will be occurring. Okay, and here is the recrystallization zone. The grain growth will not happen, but the microstructure will be changes. And partially transformation zone and tempering zone. Tempering zone, there the cementite will be converting into this graphitic segregation and takes place and changes its microstructural properties. Okay, so the experience of the next is the which of the following properties of the welding joint is most likely deteriorate due to coating of the grain in HZ. Okay, what is which property will be most likely to deteriorate once the coating of the grain happen? Which property will be reduces? First is the electrical conductivity. No, electrical conduct does not have it. Toughness, yes, could be. Next, density. No, density also do not change, and thermal expansion, that is also not change. So answer will be toughness. How? Why is that? High welding temperature can cause us to gain grain coating in HZ, which leads to reduced in impact toughness, increases the brittleness, and finer grains improves the toughness, where coarser grains decreases the resistance to crack propagation. Okay, next, in low carbon steel welding, the region of the HEZ that experiences the highest temperature below the melting point is called, okay, I think we have seen here, highest melting point below the highest temperature below the melting point. Highest temperature below the melting point, it is called as a grain growth zone. Okay, so intercritical HZ, subcritical HZ, grain coarsening HZ, and tempering HZ. Okay, it is the coarsening grain HZ. HZ in the steel often divided into several subzones depending on the peak temperature. Okay, so coarse grain HZ, we can see the closer to the fusion boundary. Subdividely, we can subdividely also closer to the fusion boundary. Very high temperature, grain growth occurs. Okay, no, the properties of this coarser grains are very high temperature, grain growth occurs and close to the fusion boundary. Next is the fine grain HZ. Next is the intercritical HZ and subcritical HZ. That is nothing but a recrystallization, partial transformation zone, and temper zone. Okay. In the width of the HZ mainly depends on the welding heat input, weld speed, thermal conductivity of the base metal, all of the above. If the welding heat input increases, the heat affected zone will be increases, width will be increases. If the welding speed increases, then heat affected zone will be reduces. It is inversely proportional. Thermal conductivity, if thermal conductivity increases, the heat affected zone will be reduces. If the more thermal conductivity means the metal will immediately dissipate that heat to the parent material, so the heat affected zone will be less. So answer will be all of them will be affected. So answer will be D. The HZ size depending on the heat distribution, which is influenced by one, heat input. Higher heat input results in higher HZ with high welding speed. Slower speed results in wider HZ, and thermal conductivity. Higher thermal conductivity, faster dissipation, narrow HZ. So all the factors influences the HZ width. Which welding condition generally produces the narrowest weld affected zone? Okay, following we have seen the four conditions. In which condition we see the narrowest heat affected zone. High heat input and low welding speed. If we give the high heat input to, as we seen previously, high heat input directly proportional to the width of the heat affected zone. So that will increases the width and low welding speed. It is also inversely proportional. So it is also uh, positive factor. So both two combinedly it will increases the heat effect zone much more higher. Okay. Next, low heat input and high welding speed. If we have the low heat input means it is inversely proportional. It will be the less heat effector zone and high welding speed. Yes, high welding speed also uh, low heat input directly proportional. A high welding speed is the inversely proportional. So that is also will reduce the heat affected zones. So both will act combinedly. So it will further reduce the heat affected zone. High heat input and a high welding speed. Okay, if we give the high heat input and high welding speed, one is the positive factor, one is the if we give the high heat input, welding heat effect zone will increase, but high welding speed will reduce it. But when so it will be at the moderate region compared to A. So A have the highest width in terms of HZ, B is the lowest, and C is the moderate. And low heat input, low welding speed. It is also will be comes into the moderate region. So answer will be the B. Low heat input and high welding speed. HZ width is minimized when less heat enters the material. Okay. Thus heat is stales and short in time. Thus low heat input plus high welding speed results in smaller HZ. This is why advanced processes such as the laser beam and electron beam produce the very narrow HZ. I think we have seen that on here, na? How this is the laser when we give the higher heat input, then here is the low heat input. How the HZ will be looks like. Okay, here is the two conditions. Hard and brittle microstructures may form HZ of the steel welds. The yes, hard and brittle metals are forms during the HZ when we do the steel welding. Which one is the uh, correct? So hard and brittle microstructure forms. Second, the reason rapid cooling after welding can produce the martensite. So both are correct or not? Yes, rapid cooling will sometimes if it's very fast cooling, then it will produce the entirely martensitic region. If it is the moderate, then partially perlite and the martensite will both will be formed. In both cases, the hardness will be increases. So answer will be A. Both A and R are true. Yes, there is a formation of the martensitic will occur in that will result in hard and brittle phase. The reason is that rapid cooling. Yes, both are correct. So you can see during the welding, rapid cooling of the steel can causes martensitic transformation. The martensitic is very hard and very brittle. Thus, HZ may is susceptible to cracking, especially cold cracking. So finally, HZ contains melting, does not melt. It HZ will not melt. Okay. Next location, it is just adjacent to the fusion zone. Microstructure, it changes due to thermal cycling because it varies with the distance. You can see here. Here is the grain growth region, recrystallization zone region, partial transformation region, and temper zone. Okay. And problems, grain growth. What is the problem with the HZ is that grain growth happening. If grain growth increases, toughness will be reduces and brittleness and cracking. Okay, control. How we can control it? Reduce the heat input or increase the welding speed, or we can do the preheat treatment or like that. Okay. Next, primary reason for changing the mechanical properties in the heat affected zone during the welding process is. What is the primary reason for changing the mechanical properties? A. Plastic deformation of the base material. B. Thermal cycling experience due to welding. C. Presence of the filler material. D. Mechanical loading during the welding. So, answer will be plastic deformation is not going to occur during the HHR formation. Okay, so that is not the reason. Thermal cycling, yes, we will provide the heat which is from the dissipating from the fusion zone that will affect the microstructure of the base material. Next is the presence of the filler material. No, filler material is not the reason. Filler material present at the fusion region, but that is not effective one. And mechanical loading during the welding. So we are not providing any mechanical loading, so that is also not the reason. So answer will be the thermal cycling experience due to welding. The HZ experience the heating and cooling cycle without melting. Thus, thermal cycling causes. Okay. So grain growth will take place. Uh, what is the reasons effects in the HZ is that grain growth taking place, phase transformation. It will change the phase to certain phases like martensitic and so benetic phase and so on, and residual stresses because of the rapid thermal contraction, expansion and contraction. Residual stresses may generate, though changes the hardness, toughness, and strength of the material. Next is the in carbon steel, the formation of the martensite in HEZ results in. So, generally, how the martensite is forming is that because of the rapid cooling. If you do the rapid cooling, the pellatic phase that once in HEZ, during the HEZ, it reaches the above recrystallization temperature, that is, it is reaching into the gamma phase region. So, from there, if it is the cooling very fastly, because of the last time, it will avoid that nose curve and reaches the martensitic phase. Okay, so the proportion of the martensitic phase is the depending on the rate of the cooling. If we cool very fast, it will be contains the 100% of the martensite. If we cool it to moderately, then it may varies with percentages vary between the perlated to martensitic. Okay, so what it is results in, martensitic generally have the higher hardness and brittleness. Okay, so increasing that answer will be increasing the toughness, no. Increasing the ductility, no, it will not increase the ductility. Increasing the hardness and brittleness, yes, hardness and brittleness will be increases. And reduction in the strength, yes, that will strength also will be increases. So answer will be the C, increasing the hardness and brittleness. When carbon steel cooled rapidly after welding, martensitic can form in HZ. Martensitic we can characterize by high hardness, low ductility, high brittleness, can lead to weld cracking. Okay. Which of the following properties most sensible to grain growth in HZ? Which property can cause us to more sensitive to grain growth in HZ is that if the grain growth increases, as we seen previously, uh, once the grain growth increases, the crack propagation path will be much more narrow and it will high prone to cracking. I think we have seen somewhere. Yeah, yeah. So grain coarsening HZ which leads to reduction in the impact toughness And finer grains improves the toughness, and where coarser grains decreases the resistance to crack propagation. Okay, so that results in reducing in the toughness. So the grain growth is mostly affects the toughness properties of the material. So explanation: the grain strengthening affects the impact toughness. The finer grains gives the higher toughness, coarser grains gives the lower toughness. Hence the HZ often experiences the grain coarsening. So how the finer grains and coarser grains increase the toughness is that if I have a coarser grains here, assume, and if I have a finer grains here, okay. So here the crack propagating path will be much more tedious compared to here. Once crack ignited, it will be can be easily propagated. But in case of finer grains, it is crack propagation will be much more tedious. So that makes it much more resistance to break. That increases its toughness. Okay. Next, hardness of the heat affected zone in alloy oil is generally higher than the base material. Due to why? So as we have discussed, one is the why hardness is increases because of the in HZ when the faster cooling happens in case of steels. So the gamma phase will some portion or fully it may convert into the martensitic phase. So martensitic phase generally have the highest hardness that results in the higher hardness. That is the so option will be first is the A grain refinement only. So if the grains are coarsening, it will change the hardness. No, that is not the reason. B formation of the if the grains are size increases, the hardness will be reduces. So the formation of the martensitic and benetic phase. Yes, those two are the very hard phases. So those will increases the hardness. And C reduction in the carbon content. No, there is no reduction in the carbon content happens. And complete melting of the material. In heat affected zone, there is no melting of the material occurs. So that is also not the reason. So answer will be the B. Formation of the martensitic and benetic formation. Okay. During the rapid cooling in welding, transformation may produce martensitic phase and benetic phase. Both are structurally hard than the ferritic and paralytic phase. That results in increasing the hardness of the HEZ. Okay. Which property of the HEZ is mainly responsible for the hydrogen induced cracking in welding joints? Okay. What is it? So hydrogen induced cracking, high ductility? No. It will not have the high ductility. Next is the low hardness. No. High residual stresses and brittle microstructure. Yes, that could be. And for D is the low thermal conductivity. So answer will be C. High residual stresses and brittle microstructure. Why is that? Hydrogen cracking occurs due to combination of diffusible hydrogen and residual stresses and hard brittle microstructure in the HEZ. Okay. So among those given one as high residual stresses, so answer will be the C. So those will contribute into the HZ. So ductility of the HZ compared to the base material is usually. So ductility will be increases or reduces. It will be because of the martensitic phase and microstructural changes. It will be reduces. So answer will be A. Higher due to recrystallization, lower due to microstructural change. C. Same as the base material. D. Independent of the welding parameters. So answer will be B. Lower due to the microstructural changes. Why? Due to the welding heat, the grain coarsening occurs. That hard paste like martensitic may form. the residual stresses develop, those factors generally leads to reducing in the ductility in the HZ. So these are the some of the properties which will be changes in the HZ. Hardness usually increases, toughness decreases, ductility decreases, and residual stresses increases. Grain size often become coarse. I think here also Sara already have given. Yeah, here is the toughness, how the toughness changes with the welding. So here is the weld fuse zone. Here toughness is the here it will start to reduces. Then because of the grain coarsening happens here. Then after recrystallization and partially transformed region and tempered region, the toughness will be increases. Then it will reaches to the similar conditions of base material. Okay. So which factors affects the how the microstructure changes is that no, this is not, this is he- heat treatment process. So here is the different transformations we have seen. So here is the different transformation: partially transformed region, tempered region, and recrystallization zone. How the microstructure looks like. Okay, the spherical particles of Fe3C will. In parallel, generally we have seen a layer kind of formation. One is the ferrite, then after cementite. Those cementite particles will become spherical in this region. Okay. The grain growth are depending upon the composition of the steel and specification of the specific heat input in the welding. In SAW process, smaller grain growth occurs because of the less heat input. But in case of SAW, submerged arc welding, higher growth occurs because of the higher heat input. The prediction of the properties of the grain growth zone is requirement to know amount of the exchange, the grain growth and the welding cycle and weld thermal cycle. Okay. Some steels such as the paralytic free steel like carbon is less than 0.9 percentage or less hardly react to effect of the thermal cycling, while some others like low carbon steel more sensitive because of the carbon steel. So if the carbon content increases, the change in the microstructure will be much more prominent. Why? Because of the carbon content. If the carbon content increases, the it will start segregating up formation of the cemented phase, and those will and formation of the martensitic phase. Those will affect the change in the microstructure. The majority of the alloy steel shows the martensitic and magnetic structures over the wide temperature interval of the cooling from 880 degrees centigrade to 500 degrees centigrade. Okay. The toughness is affected by because of the possible degradation of the plasticity in HZ due to reasons such as the aging and grain coarsening in the underbed zone. Okay, decrease in the toughness value is also related to the formation of the unfavorable microstructure in the zone, also known as the transformation embrittlement. Okay, toughness varies. Values are affected by the chemical composition, microstructure, grain size, and several other factors. Okay, Okay, coming to the next question. During the welding of the plain carbon steel, the rapid cooling of the heat affected zone most likely to produce. Which kind of was it? I think it is also we have already seen. Ferrite phase, catalytic phase, martensitic phase, and austenitic phase. So answer will be the martensitic phase. If the cooling rate is very high after welding, the martensitic phase forms into high temperature transformation into martensitic phase. Okay, the martensitic phase generally have the higher hardness, higher brittleness, and it is diffusionless transformation. Which microstructure produces a product of formation of the steel when cooling rate is moderate during the welding? Okay, if the cooling rate is too fast, it will the magnetic for martensitic formation. If it is the moderate, it will the magnetic formation. If it is the slow cooling, it is the ferrite plus perlite formation. So answer will be the magnetic formation. Different cooling rates, also magnetic. There is are also two different kind of magnetics are there. One is if we upper magnetic and lower magnetic. It is also based on the cooling rates. If it is among those two, if it is the higher cooling rate, it may forms the lower magnetic phase, and if it is a much more slower cooling, it may forms the higher magnetic phase. Different cooling rate produce the different microstructure. Granite has the higher strength than the perlite. Okay, better toughness than the martensite. So here we can see how what is the different cooling rates will produce the different kind of microstructure. Slower ferrite and perlite, moderate bayonet, and faster cooling martensitic formation. The primary microstructure forms in the fusion zone during the solidification of the steel weld metal is in the fusion zone. Which kind of microstructure it will forms? I think we have already seen here. It will be the columnar grain structure. So here you can see coarsening of the grains only happen at the HHZ region, and columnar grains we can see in the fusion zone, and base material will not be affected. So it will be the columnar dendrites. Explanation. In the fusion zone, molten metal solidifies with a temperature gradient that causes directional solidification, growth of the columnar dendritic grains. Those growth towards the direction of the heat flow. Next, in low carbon steel, the weldments, the most common microstructure, forms during the slow cooling of the HZ. I think it is also we have seen ferrite plus perlite. Slow cooling. If it is a faster cooling martensite, if it is the moderate cooling, it will be the bayonet. Which of the following microstructure is most undesirable in weldmate due to heat at brittleness? It is also ferrite. It is the much more. It is have the no brittleness, and perlite. It is the also not that much brittle. Bayonet partially, and martensite is the most brittle material. Okay, so we don't want to formation of the martensite because it will increases the hardness and brittleness. So that results in solidification susceptible to cracking. Okay, extremely higher hard. So we don't want the martensitic formation. Why is that? It is because it is very high hardness, low ductility, and susceptible to cracking. Thus, welders are often use preheatment and post-welding heat treatment to avoid the martensitic formation. So, how this preheating and post-treatment helps is that if we do the preheat treatment, the base material temperature gradient will be less. So, if the temperature gradient is less, the cooling rate will be become less. If the cooling rate is becoming less, means the formation of the martensitic phase will be low. Martensitic phase forms only during the higher cooling rate. So if we reduce the cooling rate, then also it will be happens. Second way is that post welding heat treatment. If we do the once, if it suppose in certain case, if the metastatic formation was happened in the welding, if we do the post heat treatment, so that if it is above certain temperature, recrystalline temperature, so then the metastatic phase will again convert into austenitic phase. Then if we do the normal cooling, normalization or furnace slow cooling, then again it may forms the paralytic phase that will changes it to metastatic to some other phases like perlite, so that will reduce its brittleness. Next is the a welder metal often shows the dendritic microstructure. This is the so reason solidification during the welding occurs under steep temperature gradient. So both are correct. Yes, both A and R are true because and R is the correct explanation. B, both A and R are true, but R is the not the correct explanation. C, A is true, but R is the false. D is A is false, but R is true. Both are correct actually. So during the welding, the molten metal cools under high temperature gradient and solidification occur directionally. This process retractive microstructure in the welded metal. So this is the which kind of phase forms during which kind of phase forms during the which kind of cooling rates and its properties. If you want, if you do the slow cooling rate, the formation of the ferrite and perlite is the mostly happens. Those are mostly soft, ductile, and have the moderate strength. In case of moderate cooling, we will see the formation of the barometric phase. It is the strong and tough, very high toughness. Next, martensitic phase, it is due to very rapid cooling. It is the hard and brittle phase. We don't want that to happen. We want to avoid that. Next, dendrites solidification in the fusion zone. It is directional grain growth. Okay. Next, next coming to heat treatment. So what is the heat treatment to consist of mostly? One is the what is the temperature we are reaching to the heat treatment process. Second is the what is the how much duration we are keeping at that heat treatment temperature. Next is the once we kept it, what is the cooling rate we are providing and what is the heating rate. So we can plot a graph of that one here. So is y-axis is the temperature, x-axis is the time. Okay, so what is the crucial factors for the any heat treatment process is that first is the heating rate. Heating rate means the slope at what fast it is heating up to. Second is the at what temperature we are holding it. Okay, this is the temperature, this is the time. So what temperature we are reaching and what rate we are reaching, then after how much duration we are holding it. Okay, then what is the cooling rate? It could be slower cooling or faster cooling or different cooling rate. If it is the faster cooling, it will forms the martensitic phase. We don't, and if it is the normal cooling, it will forms the paralytic moderate cooling baronetic phase, and if it is a slow cooling, it may forms the ferrite and uh, paralytic phases. Okay, so above this temperature, 1000 for a case of steels, 1050, the grain growth will started happening. Okay, so why we have to provide the preheatment? This is for the post heat treatment. So why we have to provide the preheat treatment? Reason is that decreasing the temperature gradient. First, we have to reduce the temperature gradient so that the formation of the martensitic phase and those we can avoid it, and slow down the austenitic decomposition and decreasing the zone plasticity and increasing the susceptibility of the steel to in, and if there is any grease or something, the to clean the surface also, and to so we can see the embrittlement in the HZ. Embrittlement in HZ may be avoided by using the preheat treatment and post-heat treatment. Using the preheat treatment, the total temperature drop is reduces, while the post-heat treatment is primarily aimed to stress relieving treatment. Okay, if the due to attention in the n- no pay to measure catastrophic failure of the weld structure may occur. Okay, why we have to provide the preheat treatment is that to reduce the heat loss in for welding area. Okay, to reduce the crack formation and reduce the okay. Next we can see some of the problems. The primary purpose of the preheat treatment in base metal before welding is to increase the welding speed, reduce the cooling rate of the weld region, increase the melting temperature, improve the electrical conductivity. So answer will be B, reducing the cooling rate of the weld region. X by heat treatment raises the initial temperature of the base material, which reduces the cooling rate after welding, prevents the formation of the magnetic brittle martensitic phase, and reduces the thermal stresses. Thus, preheat treatment improves the weld quality and crack resistance. Okay, next, preheatment during the welding mainly used to prevent the which type of weld defects: porosity, hard cracking, hydrogen induced cold cracking, or lack of fusion. Okay, so answer will be the C, hydrogen induced cold cracking. Why is that? Preheatment helps the reducing the cooling rate. If you reduce the cooling rate, means formation of the brittle phase will be less, and allows the hydrogen to diffuse out of the weld region and prevents the formation of the hard metallic martensitic microstructure. Thus, this significantly reduces the hydrogen induced cold cracking, especially in alloy steels. Next, post-weld treatment is mainly performed to why we perform the post-weld treatment to increase the welding temperature, to relieve the residual stresses in the weld bead, to increase the melting rate of the filler material, increase the welding current. So what except B, all are giving the reasons of before welding. So and those are the another reasons. So answer will be B. So relieving the residual stresses in weld bead. Okay, explanation. During the welding, uneven heating and cooling produces residual stresses. Okay, the post welding heat treatment involves heating the weld joint to specific temperature, then cooling it slowly to reduce the residual stresses, improve the toughness, and reduce the brittleness. person, the post welding treatment is mainly performed to increase the welding temperature. I think it is already has seen. No? Next is that which of the following process commonly used in post weld treatment for the steel welding. So which are the following process commonly used? So annealing, stress relieving, tempering, and all of the above. So it will be the all of the above. Why is that? Different post weld heat treatments includes stress relieving. We have to reduce the stresses in the weld bead. So so to prevent the cracking. Next, tempering, reduce the hardness and brittleness. Annealing, reduce the ductility, restores the ductility, and refines the microstructure. So it is choosing of the which processes depending on the material and application. Next is preheating is primarily required when welding low carbon steel with low thickness, high carbon alloy steels, pure aluminum, and copper. Preheat treatment where we required because high carbon steel is highly prone to formation of the martensitic phase. And so we want to reduce the cooling rate. So in that case, we have to provide the high carbon steel. So high carbon alloy steels generally prone to formation of magnetic phase, hydrogen cracking. So preheat treatment helps to slowing the cooling rate and reduce the hardness in HZ, allows the hydrogen escape. Next, the post welding heat treatment improves the toughness of the weld joint. The reason is that post weld heat treatment reduce the stress and tempers the brittle microstructure. Both are correct? Yes, both are correct. So why is the post welding heat treatment improves the toughness and welding joints because of its changing from microstructure metastatic to uh, paralytic or other microstructure, and it reduces the residual stresses and tempers the brittle microstructures. Okay, it is also reduce the residual stresses also. So post welding treatment reduces the residual stresses, can temper the madness rate, leads to reduced in hardness, increasing the ductility, increasing the toughness. Thus, answer is correct. So some of the features which we can get from the pre and pro heat treatment is that features like timing. Before welding we will do the preheat treatment, and post welding heat treatment we will do the after welding. Main purpose is that preheat treatment to reduce the cooling rate, and post treatment to reduce the stresses. The effect of the microstructure to prevent the formation of the martensitic phase, and in post treatment it will be the temper brittle structures. And crack prevention, prevent the cold cracking and improves the toughness.